Perfect. Thank you very much for inviting me for the topic Tailoring Adapted Ceramic Fiber Preforms by Wet Filament Winding Process. In the same way as Professor Schaffhöhner, I also come from Bayreuth and I also work in Bayreuth. The only thing is that I still drink beer and not wine, but maybe it comes later. Okay, first I want to thank Roberto and Andrea for the nice coordination of the CEM-WAVE project and of course for the European Union to fund our CEM-WAVE project. And of course I want first to thank my colleagues also in the Fraunhofer in Bayreuth, Mr. Jonathan Meyer, which is today also here, which did all the coating activities on fibers and coating on preforms. Mr. Eckert, which worked on the oxide fiber preform. Mr. Thoma, which produced the silicon carbide fiber, silicon carbide preform. And Mr. Schmidt and me, who do everywhere our hands in, and but we were quite a nice team, especially in the last 2 weeks. Now let's come to the topic. I want shortly go to the coating of the filaments, which is an important factor to the CMC manufacturing. And then we go to the CMC manufacturing. Then also very important at the end is the EBC coating of the CMC after to protect this CMC material in high temperature industrial applications. And of course, we had to look at the mechanical properties and some non-destructive testing before and after. And then I will conclude the presentation. The most important thing with ceramic matrix composites is the interface between the fiber and the matrix. Both Professor Schaffhöhner and Professor Colombo focused on carbon fiber reinforced matrix composites. The nice thing for the carbon fiber matrix composites is that carbon fiber embedded in a carbon matrix most time bring its interface with it. So you can have an influence on this interface between carbon fiber and carbon matrix, and even between carbon fiber and silicon carbide matrix if you just thermal anneal your carbon fibers to a certain extent to weaken the interface to the matrix. This is not really the case for the silicon carbide fiber or aluminum oxide fiber. Here you need an interface to weaken the bonding to the surrounding matrix. So everybody knows if you want to reinforce silicon carbide by a silicon carbide fiber and you have no interface, it's just a monolithic and a bad monolithic ceramic. So the interface is very important. So the interface most time fulfill not only one task, but several tasks. Not only maybe the coating has a function, especially to microwave absorption when you do some microwave assisted CVI, but also the coating, with the coating you can have an influence on the fiber matrix bonding, how stiff or how weak this bonding is, and this is a challenge of it. Most times the coating also cover the fibers, especially in the liquid silicon infiltration technique, as already Mr. Schaffhöhner told. When you really work with aggressive silicon melt at high temperatures, the silicon carbide fibers tend to be just be soluted in the silicon melt. So you need this interface to really protect the silicon carbide fiber from the melt. For silicon melt, it could also be oxidic melt, and therefore the coating is the most important thing. And as Andrea already mentioned, the CMC are quite expensive today. Therefore, we need also a coating technique which is which have to be very, very cost efficient. And the only thing is, in such case, to do a roll-to-roll process, as you see on the slide. So, in the case of non-oxide fibers, we focused on a multi-layer coating between boron nitride and silicon carbide, which is with the 3 alternating layered up on the silicon carbide fibers. Of course, we have some oxygen input in the system, but it's not so a problem. The good thing for this boron nitride is that it's in a crystalline phase and not in an amorphous state. So the stability at high temperature is much better. And we used the high Nicalon type S fibers for this kind of coating, and good results came out. And we have quite low thicknesses. For the CVI coating, normally we have in the 1000 nanometer or 1 micromillimeter range the thickness. Here we have quite low thicknesses, but they have some advantages, because you have, for this low thickness of interface, also a low amount of fiber breaching, which is really a problem sometimes. If we go to the future, right now it is so that the oxide fiber reinforced or aluminum oxide fiber reinforced aluminum oxide CMC work due to their high porosity, over 30%. Maybe in the future it is necessary to reduce this porosity to some lower extent, and then this oxide CMC need to have interface 2. Right now, the oxide preforms and the oxide CMC are not so depend on the aluminum phosphate interface, which could be probably work, but maybe in the future, when you really densify the matrix, the ceramic matrix structure to lower porosity levels. And here you see the results of aluminum phosphate coating. So we do have thicknesses of 80 nanometers, and even in some concave curvature cross sections of the aluminum oxide fibers will sometimes occur. We also do have sometimes 200 nanometer thicknesses. But we can do it in the same way, from roll to roll technique, so it's also a cost-efficient thing. Now, let's go to the ceramic fiber-based oxide and non-oxide preforms. The good thing is that we can use a fiber winding machine for both systems, for the oxide fiber system and even for the non-oxide fiber system. So we can handle highly stiff and brittle ceramics because we use cores which have a high diameter, coarser diameter, so your bending angle is quite so that no fiber breaks. And of course, you can here see a rectangular core, which we also used in the CEM-WAVE project to finally get some plates we saw there are some problems with this technique. Normally we used round tube cores to produce the preform material, both silicon carbide fiber, reinforced silicon carbide preforms, and aluminum oxide preforms. And this is a nice thing that you can use one technique to completely different ceramic fiber reinforced materials. Of course, the preforms using the winding technique, you have a small impact or a small possibility to get some material parameters shift, of course, to lower porosity or to higher porosity. In the case of the aluminum oxide, when you slowly change the slurry composition, and you can also change the angle of silicon carbide and aluminum oxide fibers deposit, and it's quite a nice technique to do. Again, we saw it already. It's also the reason why CMC are so important, because you have a long way to go from the fiber to the ready ceramic matrix composite. Even here, you have the fiber from the spool, which you get. Then you have to fiber coat this kind of thing, and you have to coat it so that you still can use the fiber for the filament winding. It does not make sense when you fiber coat your roving, and then you can take it out from one another. You cannot filament wind, so this is not so easy to do. But after the filament coating, we do the wet filament winding. Then, of course, you have then the thermal treatment, which is different between the oxide and non-oxide system. On the oxide system, you have the main high temperature thermal treatment is a sintering, and the main thing using porous silicon carbide fiber preform is a pyrolysis. And however, this thermal treatment is followed by the component coating or the preform coating, let's say, which is again important in the large scale to cover your material. And you can cover the material in such case that you can protect your CMC during the high temperature influences by some different kind of gases and temperatures. And of course, the coating should not fall off or do some strange things like craquelle structures and so on, where you have a slightly, where you have no coating, and at some points this is not so good. And this you have to keep an eye on. And then, of course, a CT inspection had to be done to really look at your sample, because after the long way from the preforming to the end, you can do a lot of things wrong. You can get a completely delamination of your material. You can have oxidizing. You can also have a problem with your oven system when your temperatures rise dramatically up. So, which happens also sometimes in our facility. And this you have also all keep an eye on, because everything what you do wrong at the beginning, you get at the end in this system. And again, let's have a look on the non-oxide tube binding process. Here you see the high Nicalon type S fiber coated with a polymer. It's epoxy resin polymer. The reason was to get a green body state, which you can really handle, and which you are also able to somehow put put the thing in the pyrolysis oven and so on. And the good thing on epoxy resin was that we have a very low degree of residual carbon which forms, which we normally don't want into high temperature applications. But this was in this project the compromise to do so. And we focused on the layer up angle on 75 degrees, and the tube thickness here was 2.5 millimeters. As you can see here, afterwards this material was then pyrolyzed, and again there we had the problem because on the only small amount of residual carbon we had such a weak mechanical property state that it's really like extremely thin porcelain, and we were the elephant in the porcelain shop, and this was the reason that we really didn't catch in this state the preform to cut the edges. And I always said we normally need to cut the edges because when we do some coating, or even when we want to have a denser matrix within the preform, you need also access to open porosities. But in this case, it was not so easy, so that's why we had to think about different ways. So we stabilize our silicon carbide preform, our very brittle silicon carbide preform with CVI silicon carbide, and then it was stable enough to cut the edges and do the final coating, which I described some slides later with the YAS system. And now I switch on to the oxide CMC winding process. Again, we have still a winding machine which takes the aluminum oxide fiber and winds the system on a core. And then at the end, after sintering at 1200 degrees C, you have this nice triple thing where your fiber volume is around 43%, your matrix volume 23%, and the porosity still is above 33, but with a complete different microstructure than the silicon carbide fiber preform. And we show you here some results on the final coating our preform tubes by using a YAS system. Here you see for the oxide tubes and the non-oxide tubes, the cross sections using the YAS. Again here, the advantage to use the same YAS system for complete different ceramics, but as you see, it worked quite well. And if you have any questions for the coating process, yeah, please ask Jonathan Meyer, he is here today, for more details. What is, again, in this long chain of CMC production very important, that you do not lose your properties through your process. Normally, yeah, you get the fiber with quite high tensile strength properties, and at the end, yeah, it's always surprising how low this kind of thing is at the end of this chain. And that's why it's important to look exactly on each of this process. And here, in the case of the oxide system, we could show in the C-ring test, so we just cut the tube into 10 millimeters sliced, then sliced the C-ring, the rings open to a C-ring, and then we just applied pressure on it and looked at the residual stress or strength which we get. And here you see also that we have a nice damage tolerant behavior of the aluminum oxide fibers, not through all of these curves, but most of them. And you see that even we get a slightly increase in strength when we coat this aluminum oxide system with the jas. But normally it's maybe not just the increase because when you test this kind of system with the coating, normally you should test your oxide material without the coating, but following all this high temperature sintering techniques, and maybe then you would have the same strength at the end. However, there's only no embrittlement, which can, of course, occur. We didn't see embrittlement through the jas coating, which occurred in this oxide system at 1150 degrees C, and this is a nice thing that we could say that nothing happened to the CMC, because most of the time you really get a worsening of your strength due to the processes. Of course, we did also computed tomography on this kind of parts to again make some before-after analysis of this kind of thing, and in the same way, even when you have a tube and you really go with this tube to industrial high temperature applications, you can exactly take this identical tube, make a post-mortem analysis with a computed tomography, and then you can really look at some impurities or on some small delaminations or pores, and then you can see, is there any enlargement of the delamination, or somehow get the pore region some cracks and so on. And this is a nice thing. What we should keep in mind is that the computed tomography is a technique which depends on the sample size. So when you have a 100 millimeter tube, the resolution will be at the best 60 to 50 microns, and everything or every effect which is smaller, you may not see. So this you should keep in mind. But anyhow, you can enroll this 3D volume CT images and look if your 75 angle percent, not percent, degree angle layup is still in this way you want to have it. And you can also see the turning zones there, which we wanted always to cut off. But anyhow, when exactly in this state, in the pyrolyzed state, you can't do it because the 5% residual carbon do not hold your system. It just will fall apart without any additional matrix. So in this case, it was necessary to keep these winding zones. But after the CVI, silicon carbide infiltration, we were able to cut these turning zones off. Anyhow, it's very nice to see on the CT images what errors we can do. You see in the rectangular core thing that we have here, due to the rectangular core, different tension strengths on the sides. You have maximum pressure on the fibers, and in this etching or in these etched areas, your matrix is squeezed out, and here in the plane you have almost no forces, and you have in these regions an enlargement of polymer matrix. So it was not so nice to take the rectangular core, and that's why we use the round tube in the rest of the assembly project. And the thing is, with a wet filament winding process, we can achieve really nice CMC tubes independent on the material. We could do wet chemical coating both on silicon carbide fibers and on aluminum oxide fibers. And we saw good connection, good adhesion from the YAS surface to the CMC substrates, and we have a slight increase due to the YAS coating, but the good thing is that we can do with the computed tomography very nice non-destructive testing where we can look at different stages at the long manufacturing stage, and this is important to really have an eye on your process where you can do a lot of things wrong. Thank you very much.
Thank you very much, Alexander, for your presentation. So, we have time for questions, please.
Do you know much about the crystallinity of the wet chemical deposited interfaces?
The XRD was made by Jonathan. Maybe you can tell some more details on this?
We had the crystalline hexagonal boron nitride. So this was measured on produced powder as well on the coating itself.
Great.
Other questions?
Thank you for this nice talk. And my question is, you have been using systematically micro-CT for inspection in the end. And do you have other methods such as thermal imaging or whatever in order to have some somewhat lighter but efficient defect inspection procedure?
Right now we used the computed tomography with a 60 microns resolution, depend on the larger scale of the sample. But we could do right now again smaller samples with a high resolution to about up to 3 micrometers. We didn't do it yet, but we could do it. And the thing why we did not use thermography is that some of the, especially some defects in the inner parts will not really be visible because, or in the high resolution visible, because sometimes the defects are smaller than the distance to the surface of the tube. So we can do it, but the round tube is, it's not so easy to do because normally you should in the round tube and thermography you should somehow rotate your sample, and it's not so easy. So planar it's okay, but we have some problems to enroll the whole thing for the thermography. So the CT is always the way we do. And if you are interested in really extremely small microscale microstructure in the 3D volume, we really have to cut small pieces out, be careful that we do not damage the microstructure further, and then we could do high resolution microstructure.
So in this case, it's a destructive, non-destructive testing.
Exactly. Exactly this. Yeah. Thank you very much. Yeah.
Yeah, but the point was, well...
Yeah, it's not so easy
there must be some critical defects that you have identified as being really critical for the performance of your material in the end. Mm-hmm. And the question is, what is the cheapest way to identify it as soon as you've produced your tube? That's the question.
Yeah. We did Archimedes and CT measurements for the non-destructive, and when you go really further and to really small extent of microstructure, you have to cut these materials down, and then we have no clue how to do it in a different way. Sorry. No.
We'll discuss on that later. Thank you.
I have another question. Okay.
A very easy question. Do you have any problem to release the tubes from the cores?
This was not a problem due to we took some papers and so on, but sometimes it can be that there is a problem to get it off. But in the case of the silicon carbide, it was no problem. What we do sometimes is to use also graphite cores and heat it up, and there is so that the diameter increases of the tube, and then it gets easy off. So, but sometimes it's really hard. And we had also an accident, I think 4 or 5 years ago. There was heavy machining, and then he put this tube in his in the right thing. So it's not really so easy as it sounds. So yeah, but anyhow, we get all tube from each core in the past. Anyhow.
Yeah, my question is regarding the infiltration with epoxy resins. Yeah. Have you considered some other different pre-ceramic polymer like polycarbocylene? What difference you expect and what advantage or disadvantages you may see?
Yeah, the thing is, when we use silicon polymer, which we did not use in this project, is the thing that you have to put your whole winding machine into a fully glassed surface to both get not oxygen in and not to burn your polymer off while you wind off, because it's sometimes very sensitive to air, and this is the main problem. I think it's no problem to use this silicon polymers, but from the critical point of view, or for the point of view that this is not healthy, point one, and on the second thing that it can burn off, we need to do a winding machine in a glove box, let's say. And that's why we decided to do with the epoxy resin. But of course, it would be the best way to use a silicon polymer to make it, to do a porous preform. Of course, but it's a technical problem. But we could result it, or when we use a smaller winding machine into a glove box, then we could do it. No.
Okay, let's thank again our speaker.